Okay, so so for number 7, it says that you want to paint a sphere, and I gave you a little hint at the bottom that the surface area of a sphere is 4 pi r squared. So that's what the little note at the bottom is. So if you're painting, that's going to be important. And then it says, use a linear approximation to approximate the amount of paint that you need to do the job. So did we pick up on the idea that linear approximation it's a tangent line, but it's a tangent line where you can only use values that are really, really close to the point of tangency. So you can't use other values. So if the point of tangency is at 5, you can't use the value 100. It's a tangent line where as long as you're really, really close to the point of tangency, they're going to say, oh, then the values on the tangent line are approximately the curve. And then go ahead and just use the tangent line approximation as an approximation of the curve. That's what this whole idea is saying, is that if you don't have the curve, then the tangent line approximation is good enough for us to use as an estimation. Does that make sense? That's like the big picture perspective of what we're doing. Okay. So surface area is 4 pi r squared. So they say that they want to paint a sphere, and they're doing it for a radius of 200 centimeters. So what should we plug in? Yeah, your R value is 200, your radius, so we're going to plug in 200. So what I'm doing right now is I'm finding the x and the y coordinate for my tangent line. So I'm not finding the slope, I'm just finding the x and the y coordinate for my tangent line. 200 squared is 40,000. Well, really, it's not an x and a y, it's a r in a surface area, technically. Yeah. Makes it hard to see. Okay. So if that's like the x and the y coordinate of my tangent line, how do I find the slope of my tangent line? Derivative of the surface area, okay? So this was like SA of R. So next I want SA prime of R. And so what's the derivative of that? Okay. And then I need this in the same place at the same x value. So plug in the 200. So there's my slope. So my linear approximation in terms of r is yeah, so we can do, now a lot of times, I'll go ahead and write it the way that we're used to writing it. So we've got, it's okay, we can do y minus equals slope times x minus, or in this case, r minus 200, right? And then for the tangent line approximation, or the linearization, they don't leave this as y and they don't leave this over here. They take this portion and they add it over here onto the end. That's the only difference from what we've been used to. And then instead of y, they're going to put the linearization in terms of r. Okay. So let's figure out what we're going to be plugging in right here, what it is that we're approximating. So they said that the sphere has a radius of 200 centimeters and it has a coat of paint that is 0.2 centimeters thick. So if it's 200 centimeters, it has a coat of paint that is 0.2 centimeters thick, then what should we plug in for R? 200.2. Does that make sense? So it is 200 to start with. We are taking that 200 and we are adding 0.2 to it. So it already has a radius. Its radius is not 0. Its radius is 200. We're taking that 200, we're making it a little bit more. So we are taking the 200, we're adding 0.2. No, because we're not dealing with diameter. We'd do 0.4. If we were dealing with diameter, we would do 0.4. We'd add it to both sides. But since we're dealing with radius, we only do it once. Okay. We would only do the 0.2 if we had used 0 for the radius. Does that make sense? So, but we didn't use 0 for the radius, we used 200. So we're doing 200.2 because we used the whole thing. Does that make sense why we're using 200 and the 0.2? So we didn't use a equals 0, we used a equals 200. So we're doing 200 plus the 0.2, okay? And you can kind of make sense of it because if you were to plug in just a 0.2, you would have 0.2 minus 200, and that wouldn't really make sense. That'd be a weird negative number, okay? So let's go ahead and plug this in. We're going to do L of 200.2 equals 1600 pi times 200.2 plus 16, or 160,000 pi. Oh, minus 200. I missed my minus 200. So 200.2 minus 200, that's just going to be 0.2. So these are often not calculator active problems. So how can we do this if this was like an FRQ problem when we had to do it? 2/10. So we got 160. So this is nice because this is going to cancel out with one of the zeros. What's 160 times 2? 320. Okay. So we've got 320 pi plus. So what's our final answer? And then centimeters, it's surface area. That's centimeters cubed, right? It'd be a volume. But we're talking about a thickness, right? That is very confusing. Yeah, I think it is a volume. The amount of paint. Oh, that messes with my brain.
I think amount of paint.
Yeah, it'd have to be a volume, but that still like feels very strange. Okay. All right, there's number 7. Okay. Oh, I wrote centimeters. Oh, silly Miss Rice. Okay. Okay. Done with that one. And then we said number 11. Okay. There is a typo on this one, which would be helpful if you didn't have the typo in there, so that's probably why. Okay, so let's do it together anyway, because that's my bad. Okay, your physics professor tells you that you can replace sine theta with theta, not sine 0, with theta. You can replace sine theta with just theta when theta is close to 0. Explain why this is reasonable. Okay, so you can replace sine theta with theta when theta is close to 0. Okay, so what function are we working with? What function did they mention in the problem? Sine, okay. And then what value are you plugging in for x? 0. That's the value that they're talking about being close to. So we're going to say when a equals 0, okay? So the value that they mention as far as like a tangent line approximation is they're saying when you're close to 0, apparently it's basically 0. According to this professor, it's when you get close enough to 0, then the evaluation is basically 0. And if you think about the unit circle, is that true? I have to think about this for a second. When the angle is 0, the y-coordinate is 0. Yeah, that's okay. So that's about true. But okay. So far, okay, professor, you might be onto something here. All right, so let's get our x-coordinate and y-coordinate, and then let's get our slope, and let's see if there's a reason why this professor's right, aside from just what we thought through on the unit circle. Okay. All right, so our x-coordinate is kind of this a value we just chose to plug in, right? So we're using x equals 0. And if we plug in 0 for x, y of 0 equals sine 0, that's what we just chose to think through on the unit circle. I'm going to go ahead and draw a picture for those of us who were not kind of going as quickly there with our brains. This is 0 pi radians. If we think about the x-coordinate and the y-coordinate, that's an x-coordinate of 0, a y-coordinate of 0. Sine is the y-coordinate, so that means the output is 0 as well. So if we're doing our tangent line approximation, we now have an x-coordinate of 0, we now have a y-coordinate of 0. Okay, everyone tracking so far? Okay. All right, let's go ahead and continue on with the process. What else do we need for our tangent line approximation? derivative. Okay, y prime is cos y prime of 0 is cos of 0, which is 1. Okay, so now let's go ahead and write our tangent line approximation. So our tangent line is y minus 0 equals our slope times, okay, but yeah, plus the 0 over. So L of x equals 1 times x. Okay, so what the professor was saying is he wasn't using x's, he was using thetas, right? So this is what we ended up with. So we had L of x equals x. We started off with y equals sine of x. The professor said, if you have sine of theta and you are close to 0, that basically equals theta. Is that true? Yes. Okay. Can we explain why? Because the derivative is what? 1 when the x value is 0. That's why. So that if the slope is 1, that coefficient is 1, which means whatever you plug in is what you get. Does that make sense? So the derivative is not 2. The derivative is not negative 1. The derivative is not 1/2. Since the derivative is 1, you have a coefficient of 1. Does that make sense? And so whatever you plug in for x, your input and your output are going to be exactly the same. Does that make sense? And then you have that point 0, 0, right? Which means if we think about our transformations, no left-right shift, no up-down shift. So you're not being impacted by that whatsoever. Does that make sense? Okay. So that's why the professor is right. It's just kind of hard to wrap your brain around. Okay. It's weird. It's weird. He's not wrong, but it's weird. It would have helped if I fixed that typo, wouldn't it? But then we could do it. Then we were able to do it together, so that was good. It was nice to do that together. Okay, let's go ahead and get our notes out from last night so we can finish them. It's example 3 is the one we have to finish. Is that right? Okay. All right. For the big picture perspective of linearization, how do we feel? We don't know. Find the tangent line, x-coordinate, y-coordinate, slope. Okay. As long as you can get that, you can do them. As long as you can do that, you can do them. Okay. So we did the farmer. We did this. Okay. Find the point on the parabola, y squared equals 2x, that is closest to the point 1, 4. Okay. All right. Here we go. All right, so we have y squared equals 2x. So if I wanted to isolate the y so that I could graph this, then I would square root the y. And what do I always have to do when I am square rooting? Plus minus. Okay, so I have y equals plus or minus square root of 2x. So if you can think this through, This is a square root graph looks like this. So this is the top half, square root graph, bottom half, square root graph. So y squared equals 2x, and you might have even remembered that a y squared graph is a sideways parabola. Maybe you might remember that from pre-calc. Y squared, if that's y squared and that's a positive, then that's a parabola that opens to the right. If that had been a negative 2x, that would be a parabola that opens to the left. You might remember that from conics, directrix. Does that sound familiar? No? Okay. That's cool. All right, so we've got, if we were to plug in the point 1, 1, 4, if we were to plug in the point 1, the square root, if we plug in the point 1, square root of 2 times 1 is a square root of 2. That output, square root of 2, is smaller than 4. Does that make sense? So that means that the 0.14 is higher than this. It is not on the line. The 0.14 is not on the graph. It's going to be above the graph. Okay? So they want to find the point on the parabola that is closest to this. That's the optimization that we are doing. So what we're doing, if we're finding the point that is closest to 1,4, is we are going to minimize the distance between the parabola and that point, okay? So when you optimize, you can maximize something, you can minimize something, okay? And in this case, we are going to minimize, all right? And we're going to minimize the distance between this point right here and this point right here, and I don't know what that point is, but I know that it's an x and a y coordinate, okay? So this point up here is the 0.14. I'm going to zoom in just a second. That point is 1,4. I should have drawn my picture bigger. 1,4. And this point, I don't know what it is, but I know it's xy. Okay? So we have the point 1,4. We have the point xy. Okay. Does anyone know a formula that tells me the distance between 2 points? Distance formula. Anyone remember what it is? The distance formula comes from the Pythagorean theorem. So it's going to have, it's got something squared plus something squared. All right, well, let's Google it. Get your phones out. Distance formula, what is it? Uh-huh. Uh-huh. Okay, and do you guys remember what the x2 and the x1 are? It's just 1 point versus, it's 2 subpoints, it's 1 point versus another point. Okay, so if we're talking about like x2 minus x1, it could be like, let's say, we have 2 points, right? We have xy and we have 1, 4. Does that make sense? Okay. You just have to stay consistent. Yeah, okay. So I'm going to go ahead and write out the formula real quick. So I've got x2 minus x1 squared plus y2 minus y1 squared. I'm going to zoom out just a little bit. Yeah. Uh-huh.
And I thought of it, like, so I read it, and like, so many ideas. And we thought of a label, when we like listened, and we're like, yes, maybe. We felt like more stupid.
Oh, you're fine. Do not stress it. So what we're going to do is we're going to plug in the x, y, and the 1, 2, or the 1, 4, I mean. Okay? So I'm going to do x minus 1, y minus 4. Is everybody good with that? Okay. Yes. So the reason we knew to use this formula is because they said to find the point on the parabola that's closest to the point 1, 4. So we have a point 1, 4 and then a point on the parabola x, y. And when they said to find the point that's closest, that's an optimization problem because it's maximizing or minimizing something. So that's how we knew to use that. And then we knew to use this formula because it's the distance between 2 points. So optimization is maximizing or minimizing something. You find a formula that makes sense for that problem. So if it's an area problem, use an area formula. If it's a problem that has to do with surface area, use surface area. If it's a problem that has to do with a triangle, maybe use the Pythagorean theorem, maybe use SOHCAHTOA. If it has to do with a triangle that's not a right triangle, you might use your law of sines or cosines. If it has to do with the area of a circle, you might use pi r squared. So you use formulas that you've used in the past and then just use them for the context of the problem. So this problem was just interesting because they're talking about the distance between 2 points. And it's been a long time since we've talked about the distance between 2 points. But this is the only formula that we know that makes sense for a problem to find the distance between 2 points, right? This is just like the only thing that would make sense for this, yeah. Yeah. Uh-huh. 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 So it would be any x and y. It'd be any 2 points. We're using it for these 2 points specifically, and the way that we're going to know if it minimizes is going back to our sign chart. Does that make sense? Is if our sign chart does a minus to a plus, then we know that it minimizes. Does that make sense? Okay. All right. So if I'm working with this problem, then what I want to do next is I want to try to deal with 1 variable instead of 2. So right now I have distance in terms of x and y. Does that make sense? And I only want to either have distance in terms of x or distance in terms of y. Okay, you can do the problem either way. So if we go back to the original problem, we can either we can take this y, which would be kind of difficult because of the plus minus. Does that make sense? So if we wanted to get rid of the y and have the whole problem in terms of x, then we'd have to have a plus minus right there, plus minus root 2x. Does that make sense? Or what we can do is isolate this x, divide the 2 over, and then take the x and plug it in right there. Does that make sense? So we can use that original equation to help us narrow down the problem so it's only in terms of 1 variable and not in terms of 2 variables. Does that make sense? Okay, yes. We wouldn't do that only because technically y minus 4 squared, if you were to FOIL this out, it would have a y squared in it, but it would also have a y in it. And that's why we wouldn't want to use that, because y squared isn't the only thing we're working with. Does that make sense? Okay. So what I'm going to do is I'm going to take this right here. I'm going to say y squared equals 2x. I'm going to divide by 2 so that the x is isolated. And so now, since the x is isolated, I'm going to take that, and I'm going to take this x and replace it with y squared over 2. Okay? So the whole purpose of that was to get this in terms of one variable. I could have gotten it in terms of x, I could have gotten it in terms of y. It was a little bit easier to do in terms of y because the x had that plus minus with it. Okay? All right. Now, for me to maximize or minimize this, I need to be able to take the derivative. It's going to be a little bit easier for me to take the derivative if I get rid of this radical. And I can maximize a d squared just as easily as I can maximize a d. All right, maximizing an area versus maximizing a length of something is going to work the same way. So what I'm going to do is I'm going to square both sides. So I'm going to say d squared equals y squared over 2 minus 1 plus y minus 4 squared. So this was taking, I went back to the original problem, and I just isolated, yeah, I did substitution so that I could get it written in terms of one variable. Okay. So at this point, I am ready to do my derivative, and that's where I'm going to do my actual maximum and minimum, or minimum, right? Because I will only know if it's a maximum or a minimum once I do my sign chart, okay? So let's go ahead and do my derivative. So I'm going to say the derivative of the left side, so I'm doing prime, all right? How do I do the derivative of the first piece? So derivative of the outside, keep the inside the same. Times, what's the derivative of the inside? 2 times, wait. 2 times 1/2, why? That hurts my brain. I'm just going to write it. I'm just going to write it because it hurts my brain way too much. Okay. You don't have to do dy dx because it's kind of working as like your x value. Yeah. All right, plus 2 y minus 4 to the 1 times 1. Okay. Okay. So we can go ahead and do all of our distributing, right? So this is we got a 2y that's being multiplied inside. I'm just going to write it so it's easier for me to do my distributing. Okay. So there is that's my derivative once I've multiplied everything out. And then what do I do with my derivative? To find a maximum or a minimum, set it equal to 0, right? Because I'm finding my critical points, right? That's how we always find a maximum or a minimum, is we find our critical points. So set it equal to 0. Yeah, you actually don't need to solve this by factoring. You can solve it by taking roots. So we can just add the 8 over to the other side. So y cubed equals 8. And then what do we do? Cube root. So y equals 2. Okay, so now we can do our sign chart too. Y cubed minus 8 is what we're plugging the number into. There's our sign chart. So I'll use 0 and 3. 0 cubed minus 8, negative. 3 cubed minus 8. Okay, so what does that tell us? It is a minimum. Okay, so we chose a y coordinate of 2. We got that it definitely is a minimum, so we have minimized the distance. Okay, so we have correctly done what we set out to do. So now we need to find our x coordinate. So plug it back in. We'll go ahead and zoom out. So we got y equals, we got 2 squared equals 2x. 4 equals 2x. And so what does x equal? X equals 2. All that work to find 2. 2, 2 minimizes the distance to 1, 4. That's a lot of work. Okay. What point were you confused about? Okay, so big picture perspective. Big picture perspective is we looked at what we set out to do. We kind of drew a picture, right? We figured out a formula that works. So our formula, what we figured out was that we had 2 points, and we needed to find the distance between them, and we needed to minimize that. So that was the. So I think that's the hardest part, is even knowing what formula you could possibly use. So the distance formula. Once we had the distance formula, we took an equation that we originally had, which is kind of an important piece, because I think this is the piece that students usually have a hard time with, is that oftentimes there are 2 formulas at play, and this original formula helped us to narrow the problem down to 1 variable instead of 2. So that was where a substitution took place to help us narrow down the problem to 1 variable instead of 2. Does that make sense? So big picture perspective, that's what we were doing. So we found a formula to work with that we were going to minimize. We used the other formula to help us narrow down to 1 variable. And then from there we were saying, okay, let's take the derivative. Let's relate it back to that curve sketching unit. We said when we take the derivative of something, that derivative is helping us find the critical points. To find those critical points, we set it equal to 0. That's the critical point. And then we use a sign chart, and the sign chart helps us figure out if it's a maximum or minimum. And when we found that and we saw that it was a minimum, that told us that we had minimized the distance between the 2 points. And we knew that we had done that because we were taking the derivative of the distance formula. So when we found that that was a minimum, and it was a minimum from the distance formula, that meant we had minimized the 2 points because we had used 2 points in the distance formula. So we had minimized the distance between the 2 points. Does that make sense? So that's kind of the big picture perspective, is we have a formula, we might have another equation that helps us narrow it down to 1 variable, And then we use that critical point idea with the maximum and minimum idea to help us figure out how we've optimized it. Does that make sense? Okay. Derivative because of the idea of a critical point and a maximum or minimum. Because optimization is always about you're maximizing or you're minimizing something. So this is tying together last unit with a maximum or minimum and bringing it into a story problem. So we have to do the derivative because the derivative is how we find a critical point. A critical point is how we find a max or min. And optimization is all about finding a maximizing or minimizing something. Does that make sense? No. Because you could find the distance between the 2 points, but you wouldn't know if it was maximizing or minimizing it. That's where the calculus comes in. It wouldn't have been a calculus problem if they hadn't asked you to minimize the distance. So if they said, find a point on the parabola that's like by 1,4, then you'd be like, let me graph that parabola and find some points on it, and I'm good to go. But as soon as they said find one that's closest to 1,4, then you say, now I need a minimum, now I need calculus, because the way that I find a minimum value is I use calculus to do it. No. Mm-mm. Minimizing is saying critical value, take the derivative, find the critical point, then use your sign chart to make sure it's a minimum. So you're not finding the vertex, you're taking the derivative, finding the critical point, and then making sure it's a relative minimum. 2, 2, 2, 2 is this point right here. So if you were to take the derivative of the distance formula, which would have been some funky, it would not have been this. It would not have been this at all. It wouldn't have been related to that at all. It would have been something completely different. If you had taken that and graphed it, it would have looked like a minimum on that graph, but we didn't see that graph. Yeah. So if they had said the 0.1 -4, then that would have been the 0.2 -2. Yeah. Yes. Yes. Any other conceptual questions I can help with? Okay, so the printer, the copy machine is like running out of toner. So they asked us not to make copies if we could avoid it, and I can avoid, like, we don't have to make copies because we can just look on Canvas. So we're going to look on Canvas for today's assignment. I'm not going to assign all of the problems. We're just going to do some of them, okay? So let's kind of look at that question. If it gave us a maximum, then we would say you cannot minimize. Can't be found or something like that. Usually what ends up happening, hey guys, that was a really good question. So Reagan said, what if you had done the whole problem and then you got down here and the answer maximized instead of minimized? Like this question, this exact question, what if they said find the point that's furthest away from 1,4? Can we even find it? No, because parabolas go forever, right? So as soon as you think you find a point that's furthest away from 1,4, you wouldn't be able to find it because then they could just draw the parabola further away, and then you'd be like, I found it, and then somebody would be like, I drew the parabola a little bit further, so you didn't. You know what I mean? So if they said find the point furthest from 1,4, and they'd be like, well, you can't find the maximum, but you can find the minimum, then you'd say like that can't be found. So typically, this part is it's going to be like, yep, I found the minimum, because that's all you can find from this problem. Usually it's confirming what you already know. It's like you're checking a box that like, okay, yeah, because that's the only thing you could find. Yeah, yes. No, you still would have been using the distance formula because it's still asking something like that. Yeah, if it said maximum, you could still say, I mean, you'd have to prove it. Yes, and you would prove it. No, because if you did that, you'd be using intuition, and mathematicians will never let you use intuition to explain.
But there's like the line between
Because this is the mathematical reason why it doesn't work, because there's no maximum. There's a minimum only, there's no maximum. So if you're using any reason to explain why it doesn't work other than this, you're using common sense and intuition to explain why. No, you're using intuition. You're saying it doesn't make sense. They're saying, show me why. The reason why is because there's no maximum. There's only a minimum. Does that make sense? A mathematician would logic and reason you all over the place with that. You guys, they're so pretentious they can do that sort of thing. You'd be in a puddle crying, you'd know you were right, and they'd make you think you were wrong, and you'd be questioning your whole life story. Okay? I promise you.